One of the keys to performing a good hypothesis test is understanding the business context for which you are creating the test and then applying the test correctly. In this video, we will use the example of testing a new in-house sales process to see if it is more effective or perhaps less effective than the old process of just calling our customers on the phone. Let's say that we have the opportunity to evaluate a new video, think Skype for Business, system that would allow the sales rep to see the customer and provide product images and related materials for a 90-day period. If we can determine that it is more successful, we will likely purchase the new system. To begin, we will take a random sample of the sales calls using the new system to see if the average order placed is different from our current average order of about $450 per call. The first step is to set up the hypotheses statements. We start by stating this hypothesis in a non-technical terminology. That is there statistical evidence that the mean or average dollar value of the orders placed with the new system is different from the orders placed with the old system, which had a mean of 450. Now we can write this in the symbolic form that you see here. Note that our non-technical statement goes with the alternative hypothesis, or H1, as that is the hypothesis that we are collecting data to prove. The HO, or null hypothesis, goes with the status quo for our current mean sales order of 450. Now the next step is to select a sample size and determine a level of significance for our test. Let's use a sample size of n equals 100 and an alpha significance level of 0.05 or 5%. While we might actually have data on the population of all sales orders in the recent past, let's assume we do not. So we will use the t-distribution for this, which is why these types of tests are often called t-tests. That means we will use this formula. Note that the x-bar is our sample mean of the data we collect. Mu sub x is the population mean of 450 that we're assuming. S is the standard deviation of our sample, or sample standard deviation. N is our sample size, and for reference, S divided by the square root of n is called our standard error of the mean, which is just a fancy way of saying the standard deviation for all possible sample means that we could take with a sample size of 100. We can also set up a rejection region to help us better see and understand whether our sample data is significantly different enough from our current mean of 450. As you can see in this display, we need to have a sample t-value in the red area in order to reject HO. This is often written as reject HO if t is less than negative 1.984 or if t is greater than positive 1.984. Now let's say that we've taken our random sample of 100 and calculated the following sample statistics. We then plug these numbers into our t formula to get the following. Since 2.50 is greater than 1.984, we reject HO. Therefore, we can conclude that the new sample mean average sales is now different from 450. We can further conclude that the mean sample sales is also greater than 450 because the sample mean of 500 is greater than our old mean of 450. We could perform another test to more specifically prove this. Furthermore, we can also provide a clear managerial statement like the following. There is statistical evidence that the mean sales from the new system is greater than 500 at the 0.05 level of significance. Here is some computer output from Minitab. The Minitab output provides a confidence interval better written as $460 is less than or equal to our population mean sales, which is less than or equal to $539, approximately. Notice that the hypothesized mean value of 450 is not included within the interval. This should go hand in hand with our statistical decision to not reject HO. Most statistical software will also provide a p-value. The p-value is extremely important with respect to helping us make our statistical decision whether to reject HO or not reject HO. Here you can see that the p-value of 0.014 comes from adding up both tail areas associated with our test statistic of 2.5. Since our alternative hypothesis had a not equal sign, we must account for both sides of 0.